In this screencast, we'll continue our discussion of Gődel numbers. So let's take a look at the big picture, step back from the low-level details. What do Gődel numbers give us? So let's say that we have a program, some program, and we have been using the formalism known as the L language, which is the language developed in the book by Davis, Waker, and Segal, Computability, Complexity, and Languages. But it can be C, C++, Java, or first-order predicate calculus, Python, Perl, whatever your favorite programming formalism is. So we're going to take some statements written in that formalism and pass it to a Gődel coder. That's, let's say that it's a black box whose internals we will develop that will take that program and convert it into a number. Right? Just one natural number can be very large and will be very large natural number typically. And then that number will be given to the universal program. And that universal program will execute it. All right, a universal machine. Right. And will output another number, or it will not output anything. Will just run forever or crash, so the output will not be defined. That number can also be given to Gődel decoder, and that'll take the number and compute the statement of the program. So, so what are the components of this big picture? So Gődel coder may be compared to the compiler, right? Because that's what compilers do. They basically translate programs into numbers, bytes. The Gődel decoder can be compared to the reverse compiler. So there's a process of reverse compilation where you get the compiled program and try to get the original source code. And the universal program executive or universal machine can be compared to the digital computer or operating system or virtual machine or interpreter. So that's the big picture of why computer scientists should care about Gődel numbers, because they essentially give us the mathematical theory of program compilation and execution. So just to remind you that let's say if we have a sequence of numbers, natural numbers, a1 through an, then the Gődel number that corresponds to that sequence, right, a sub I is a natural number, is written as in this array notation, square bracket notation, a1 through an, and it is defined as a product of the prime numbers, consecutive primes raised to the powers, corresponding powers that are specified by a1 through an. So p sub I, this is the ith prime, raised to the power of a sub I. So this is p sub I is the ith prime in this notation. So, for example, given a sequence 1, 2, 3, the Gődel number corresponds to that sequence is the first prime raised to the power of 1, the second prime raised to the power of 2, and the third prime raised to the power of 3. Just to the first, through the second, 5 to the second, 2, 9, 25. Oops, I made a mistake. It should be 5 to the third. Let's erase this and write 5 to the third, and that gives us 125, not 25. Okay. So that gives us, let me grab my calculator, 2250. Now for each value of n, the computation of the corresponding Gődel number is primitive recursive. That's for every n, where a1 through an are natural numbers, because computing the ith prime is primitive recursive, as we showed in one of our previous screencasts. Then the power function on natural numbers is also primitive recursive. And then so this is a composition, right? P to the I and raised to the power a to the I is a composition of p sub I and the power function, and the product, the bound product of p to the I, pi raised to the ith power is also primitive recursive. So it is a primitive recursive function. So let's talk about padding Gődel numbers with zeros from the right and from the left. So padding Gődel numbers with zeros from the right is harmless. In other words, it doesn't give us any new numbers, right? Why? Well, because any prime raised to the power of 0 is going to be 1. So we're just padding ones, multiplying by 1 from the on the right, which doesn't change the number, because p, the first prime raised to the power of a sub 1, and then times the nth prime raised to the power of a sub n is the same as p sub 1 raised to the power of a sub 1 times p sub n raised to the power of a sub n times p sub n plus 1 raised to the power of 0 times p sub, let's say we have k zeros, p sub n plus k raised to the power of 0. So because this is all going to be 1, so it's going to be the same number. Now padding from the left is different because that actually changes the Gődel number. Because all of the prime powers are shifted right, by the number of zeros that we pad on the left. So, and in general, so say if we pad with 1 0 on the left, it's not going to be the same as the same Gődel number with the same prime powers, but without any 0 at the beginning. Right, so this is the left number, and that's not going to be equal to p sub 1 raised to the power of a sub 1 times p sub n raised to the power of a sub n. Right, so just if you want to convince yourself of that fact, here's a simple example. 1 2 is not the same as 0 1 2. Right, the Gődel number. So it's 2 to the first times 3 to the second is not equal to 3 to the first times 1 2, right, 5 to the second. Okay, so now we have Gődel numbers. Now we need to define access functions. The access function allows us to get to the individual elements of the Gődel numbers. So if you think of Gődel numbers as arrays, then we need an array access function, right? If you think about it as a computer scientist. So the access function is going to be defined as in this notation. So the parentheses, then x is a Gődel number, and sub I is the element, the ith element, where I is less than or equal to n, but n greater than or equal to 1. So, for example, if x Gődel number is equal to this, 2, 4, 3, the elements, so then x sub 1 is 2, x sub 2 is 4, and then x sub 3, the third element, is 3. Okay, so this is the function that we will define. And so here's a lemma that the access function for Gődel numbers is primitive recursive. And so let's define it. So the access function, so the ith element is equal to the minimum t, where t is less than or equal to x, such that the ith prime raised to the power of t plus 1 does not divide x. So the 0th element of any Gődel number is defined to be 0, and any component of 0 is defined to be 0 for all i's. So here's a simple example. So 18 is equal to the Gődel number of the value of 1 and 2, right? 2 to the first times 3 to the second. So what's the first element of the Gődel number whose value is 18? And that is by definition minimal t less than or equal to 18, such that the first prime raised to the power of t plus 1, right, does not divide 18. So the first prime is 2. 2 to the 0 obviously divides 18, so that's a yes. Well, how about 2 to the first? We test the next power. Yes, it does divide 18. Yes, but 2 to the second, right, we increment t by 1, right? 2 to the second does not divide 18, so it's a no. So t is equal to 1. So we keep incrementing t, the power of the corresponding prime, and as soon as we get to the power that does not divide the number, we just return the previous value of that power of t. So same as 18, the second element of the Gődel number 18 is equal to 2, because 3 to the second divides 18, but 3 to the third does not. Okay, this is to be continued.